Next, we are going to use Biot-Savart law as we had it from the, again, from an experimental result. And we are going to use it for a specific example. And in this case, we are assuming that we are dealing with a straight, long wire. Okay, so again, this is the assumption: long, straight wire. When we have that, this equation will turn into much easier equation. Okay, so since this is a nice symmetric case and it's not bent and such, and you will see that it's not going to be as complicated as this equation above, but we are going to start from there. So first of all, this is the vector form. The first thing you do is get rid of the vectors, right? So let's write the magnitude form. So this is the magnitude of Biot-Savart. It is not a W, it's V. Okay, so we have dB. I'm getting rid of that vector sign on top of it. So we will talk about how we do the right-hand rule. It's similar. It's just a cross product. We will talk about that again to find out the direction of the magnetic field. But first, let's find out the magnitude of B field. Okay. So again, first thing we do is we are going to write this in magnitude form. So I have mu naught I over 4 pi, right? And the tricky part is ds cross r hat. Okay, so we have the magnitude of the first term, ds. First vector is ds, and then magnitude of the second vector. Some of you will think that it's r, but it's not a r vector. It's a unit vector. Unit vector have a magnitude of 1, right? And that's why we have 1, and then the sign function between them, okay? And divided by r squared. Okay, so this is really important here because I always see every year there's an issue here. R hat has a magnitude of 1, okay? Let's write it here. R hat magnitude is 1, not r, okay? And so here again we will integrate, but we gotta get our equation ready first. So let's use some geometry. We did similar stuff with electric field, so it should be so you should have better idea now what to do. So we are integrating over ds, but you can see that there is r, and the ds element changes, r changes, so we gotta write the r in terms of s. So what is r? You can think of r squared, right? So you can see this triangle here, right triangle. R squared is what? S squared plus r squared. And if we needed, r is root of that. Right? And then another geometry that we need is sine theta. So because theta is also changing when you take another ds element along the wire for this point P, theta is changing, right? So let's write that in terms of s as well, so we can integrate over s. And here we have, first of all, the identity is sine theta is equal to sine theta 180 minus theta, okay? And right here is 180 minus theta, right? So what is sine theta then? Which is sine 180 minus theta. It is r over little r. What is little r? It is s squared plus r squared, as we just wrote above, right? So that is what sine theta is. Now we are going to change our r and sine theta in the equation. So let's do that. You have room for the next page as well. So make sure to see that. So dB is, so let's put these together first. mu naught I over 4 pi. And so we have the ds, right? I'm going to put the ds at the end. Sine theta is going to bring r. So we have r here and ds. I'm going to put the rest at the bottom. Sine theta still has that root of s squared plus r squared, and r squared had s squared plus r squared. So when you multiply s squared plus r squared and that s squared plus r squared root, you are going to have, you're adding up the powers, right? 1 plus 1/2 is 3/2. And that's what we're gonna get right before integration. Now let's think about this. Can we integrate this? We're integrating over s, and as you can see, the only variable we have is s in the equation. Everything else is constant. Capital R is a constant. We don't have a little r, which depends on s. So we are in good shape. Next, let's take the integral of both sides, right? Left side becomes b, and right side we can take the things that are constant out of the integral. So we're going to have mu naught I r over 4 pi, and so we took everything out which are constant, and then we have ds over s squared plus r squared 3/2. Since we have infinitely long wire, we would go from negative infinity to positive infinity, and we need to scan everything on that wire. So instead of doing that, we can change our intervals from 0 to infinity. That means from the bottom half, the contribution coming from the bottom half needs to be contributed, it needs to be added, right? So if we only do half of it, we are going to get half of the magnetic field, right? So we need to multiply this by 2 for that reason, because I am changing the interval, and that will give me half the magnetic field. So if I multiply by 2, these two will be equal to each other, okay? These two integrals. So then I have still this. And this integral is something we've done it before a few times. So what we are getting here is 2 mu naught I r over 4 pi. And this integral gives us s over s squared plus r squared to 1/2. And again, this goes from 0 to infinity. And we're almost there. So we're gonna put these in the integral intervals in, the limits in, and then we're gonna get 2's are gonna go away. We're gonna cancel the 2's, mu naught I. We are gonna get r at the bottom, and the s's will go away. So we have mu naught I 2 pi r as the B field. Okay, after plugging in those first infinity, and then minus that 0 for s, and then see if you can get this answer from this integral.